All right, today we're going to tackle a really powerful, kind of abstract idea from mathematics called Hoehnke categories. Now, I know that sounds super complex, right? But stick with me because it was actually invented to solve a problem that's way more common than you'd think. And in doing so, it gave us a completely new way to look at, well, almost any complex system. So let's get into it.
So, let me start by throwing a bit of a puzzle at you. Picture this. You have to describe an entire city. I'm talking its rules, its flow, its very soul. But here's the catch. You're not allowed to mention a single person or a car or even a building. How on earth would you even begin to do that? Well, believe it or not, this is almost the exact kind of thinking that led mathematicians to come up with Hoehnke categories in the first place.
Okay, so where does our story begin? Well, interestingly, it's not in some dusty old math library. It actually starts in the super fast-paced, rapidly expanding world of computer science.
So, let's rewind to the 1970s. Computer science is just exploding, right? It's really taking off. But as it grew, researchers started to hit a major wall. The math tools they had, they were just too clumsy. They couldn't cleanly describe these new kinds of systems that were popping up everywhere. What they really needed was a whole new language for something called partial algebras.
Okay, I know what you're thinking. Partial algebra. What in the world is that? But it's actually a really simple idea, I promise. Just think about a calculator on your phone. You can add 2 plus 2, no problem. You can subtract 5 from 10, easy. But what happens if you try to divide a number by 0? The calculator just says, error, right? The operation is undefined. And that right there is the core idea of a partial algebra. It's just a system where some of the rules, some of the operations, don't always work for every single input. And let me tell you, computer science is absolutely full of situations just like that.
So to get around this problem, a brilliant mathematician named Hans Jurgen Hoehnke came along with a totally radical shift in perspective. He basically said, hey, what if we're looking at this all wrong? Instead of getting bogged down in all the tiny little details, why don't we just zoom out and look at the big picture?
And this analogy just brings the idea to life. The old way of doing things, what we'd call the element-based view, that's like trying to understand New York City by making a list of every single person, every apartment, and every taxicab. I mean, you'd have an insane amount of data, but you wouldn't have any real understanding of the city. Hoehnke's idea, this element-free view, is like looking at the subway map instead. It doesn't show you a single person on the train, right? But what it does show you is the structure, the connections, the rules of the whole system. It shows you how the city actually works.
And that, right there, was his mission. He put it in his own words. His goal was to create a language, an element-free language, that could describe the rules of these partial algebras. He wanted to create the subway map for these complex systems without ever having to talk about a single element or writer.
And that's it. That is exactly what a Hoehnke category is. It's the formal mathematical tool that takes this whole element-free idea and makes it a reality. It uses this really powerful branch of math called category theory to focus only on the structure, the connections, the big picture stuff.
So you might be wondering, how did Hoehnke actually build this thing? I mean, where did he even start? Well, he didn't do it in a vacuum. He really stood on the shoulders of giants and pieced together a seriously powerful mathematical toolkit. Now look, you don't need to be a math genius to follow the basic recipe here. First, he laid a foundation using category theory. Then, he really cleverly built on the concepts of another big name, F.W. Lovre. He used some other advanced frameworks to tie it all together, and bam, he defined what he called a partial theory. You can just think of all this as the technical engine under the hood, the gears that make this whole element-free idea actually run.
All right, so this all happened back in the 70s. It's pretty abstract stuff. So why are we even talking about it today? Why does it still matter? Well, the simple answer is that it gave mathematicians and computer scientists a totally new and way more powerful way of seeing the world.
His work wasn't just some small discovery. It had a massive ripple effect. For one thing, he basically provided a meta-theorem. Think of it like a master key that could suddenly unlock all sorts of new proofs. It went on to influence a whole generation of researchers in algebra. And the ideas were so potent, so necessary, that other brilliant minds were actually working on parallel tracks at the exact same time. Eventually, all this groundbreaking work was brought together in one huge, influential book that really cemented his legacy.
I mean, this book was the real deal. It took decades of his research and just solidified it into one single, powerful contribution to the field.
But here's the most crucial point, the thing I really want you to take away from all this. Hoehnke didn't just come up with a new formula or a clever trick. He gave us a whole new level of abstraction. He gave us a way to step back from the messy, confusing details and finally see the elegant, simple structure underneath it all. Honestly, it's like a superpower for taming complexity.
And so that leaves me with one final question for you. Think about some complex problem in your own life. It could be at work, at school, anywhere. What would happen if you just stopped? Stopped focusing on all the individual details, the elements, and instead tried to draw the subway map? What are the underlying rules, the real connections? What would your element-free view of that problem reveal? It's something to think about.